Good morning, class. So today our lesson is on exponential equations. So you should all have a note, and you'll notice that the top box is a review section. So this is reviewing some of our key operations that we learned in the previous lessons. So I would invite you, if you haven't done so already, to pause the video and actually attempt those questions. Understanding just those basic operations will really help you with the rest of this note. So there are going to be some new techniques in solving equations that you'll need the algebraic knowledge for. So pause the video and then I'll take them up. All right, so now assuming that you have that complete, I will share my screen with you. So let's go through these. So basically, we're rewriting in logarithmic form. It's really crucial that you're able to go between exponential form and logarithmic form. So in this case, those are the answers there. Just remember the base of the exponent is the same as the base of the logarithm. That's usually how I kind of start thinking about it. So when you're solving for logs like this, you think 2 to the power of what equals 8. So it's 3. 4 to the power of what is 1 over 16. So my first hint is that this is going to be a negative solution since I have a fraction, which flips the base. And so 4 squared is 16. So 4 to the negative 2 is 1 over 16. And then here we're using our laws of logarithms, which we will be using very often in this lesson. So first of all, when you have an exponent, you can bring it out front as a coefficient. That will be very useful for us today, which is happening in all of these cases. Now just notice that in this last one, x plus 1, that entire sum is the exponent. So the entire sum becomes the what should I say, the coefficient. So if you were expanding this would become x log 12 plus log 12. Oops, I'll just push that back. So this is crucial to understand, especially coming up in example 4 in the note. And remember that logs are just numbers. So like log 12, you can take out your calculator and find that log 12 is just a number. It's 1.079, etc. So when we are solving equations such as these, we're going to have to really train ourselves to remember that. Okay, so today we're going to be solving exponential equations. So look at this question. So this is a very typical question we would have gotten in grade 11. I think you've already gotten some of them this year, and we've solved them using estimation. So let's just take a look at what type of problem would actually be posed to result in this type of formula. So this is a half-life equation on the right. We know it's half-life because the base is a half, which means the numbers constantly being multiplied by a half over and over and over. So we start with 200 of some kind of specimen, and we actually don't know the half-life. We know that 16 units of time have passed, so either 16 hours, 16 minutes, 16 seconds. And we know that this 200 has been reduced to 12.5. So the question is, how long is a half-life? So this question, if you could actually do this with trial and error relatively simply, because if you take 200 to 100 to 50 to 25 to 12.5, you can get there on your own. However, we're going to actually solve this using two different methods so that when things do become more challenging and the answer is not an integer, we have these techniques. So I'm going to show you two methods. One is using exponents and one is using logarithms. So your solutions should look like mine if you can see me in the corner, like one solution in this column and one solution in this column. Because I'm doing it on Word, I think I'm going to have to do both of them just under method 1. Just so you know. Okay, so the key idea of using exponents, we want to solve this equation. So I'm going to start by just actually rewriting the equation. 12.5 equals 200, 1/2. Oh, sorry, I thought that was going to be in an equation. Just a second. So 12.5 equals 200, 1/2 to the power 16 over h. Okay, so the key idea here is that we want to create a common base on the left side and the right side. So notice right now, so right now we have just a number on the left and then a number times a power on the right. So the first thing that we're going to do is actually do 12.5 divided by 200 to get rid of the coefficient on. By the way, guys, I decided that this was better than trying to draw on the screen for this. So we're going to try out this way. We'll see which one you guys like better. Okay, so what am I doing here? So 12.5 divided by 200 is, what is that? So there's a couple ways to make that fraction into the smallest possible. So one way is to do 12.5 divided by 200. You'll get a decimal. And then you can use the F to D function, which is just kitty corner from the second button. You'll see F to D, which goes from a decimal to a fraction. So 12.5 over 200 is actually 1 over 16. So why is it important that I am writing this as 1 over 16? Well, the whole idea of this solution is that I want to create left side and right side with a common base. I want to have the same base on both sides. So 1 over 16 can actually be rewritten with a base of 1/2. Okay, so 1 over 16 is actually 1/2 to the power 4. Okay, so now I'm setting that equal to 1/2 to the power 16 over h. So again, why is this important? This is important because now, let me zoom in here. If I have an equality and my bases are the same, then that means that my exponents have to be the same. So I got rid of the coefficient here at the beginning. So I just have two bases that are the same here. And so that means I can set the exponents equal to each other because it says the equation is equal. So sorry about that, just a second. 4 is equal to 16 over h. Okay, and so then that means, that, I don't know why it does that. That's really bugging me. Okay, h is equal to 4. All right, so we've solved that. Okay, so that method works, but it really only works well if you happen to have a case like this where the answer is an integer. If you have answers that are decimals or in between, then it really is not an efficient way of solving. It's really quite a pain. So this means that the half-life is 4 units of time. So 4 of those 4-hour periods had occurred to get 200 down to 12.5. Okay, so now there is another method using logarithms. So the idea here is to rewrite this formula in the form y equals x to the a. So in other words, you have just a number equaling a power, and then you're going to take the log of both sides. So remember, that's why I said that up here. So if you perform the same operation to both sides, the equality holds. So now we're going to write this solution under here, but unfortunately it will show up over here. I apologize for that. Okay, so first things first, rewrite the equation, same thing. And your the first thing you do is actually the same as in this equation. You want to get everything on this side, okay? So you want it to get just a number equaling a power. So the nice thing with this, now when I insert these equations, they're going to show up on the right. I don't know why. Hopefully you guys can follow along. The nice thing about this is we can actually use decimals because we're going to be using our calculator more. So 12.5 divided by 200 is 0.0625, and that's equal to 0.5 to the power 16 over h. Okay, so notice that I am using decimals in both cases, and that is fine. Okay, that should actually show up as an exponent. There we go. All right, so now we have a case where we have, there we go, where we have just a number equaling a power. So now we are going to take the log of both sides. So we're going to write log of 0.0625 equals log of 0.5 to the power 16 over h. Now, why would we do this? You might be saying to yourself, Mrs. Weens, why are we taking the log of both sides? Because when we take the log of both sides, when we take the log of the right side, this 16 over h can be moved down as a coefficient according to our rules of logarithms. And that is really important because now that means that that unknown, the variable, is down where everybody else is, and we can solve for that variable in a way that we're accustomed to. The problem right now is that the unknown is in an exponent. So by making it a coefficient, we can solve for it. So the right-hand side is going to remain the same right now, but this 16 over h, we bring down as a coefficient. Okay. So that's really important because now we can solve for h. So I multiply h up so that it's on the other side. So h times log of 0.0625 equals 16 times log of 0.5. Now remember, these logs are just numbers. So now we can isolate h. Okay, so h is equal to 16 times log of 0.5 divided by log of 0.0625. All right, and so now this is just a matter of putting it into your calculator properly, making sure that you're putting brackets where they need to go, and you will get that h is equal to 4. Now, this seems like a little bit of, a long process when the solution on the left-hand side was a shorter process. But remember, that solution on the left side was a shorter process because the answer was an integer. So most commonly, it won't be. So this method is like, will work every time. So the idea, again, the major idea is you take your equation, you create it in the form number equals power. So no more coefficients or adding or subtracting numbers, just number equals power. And then you take the log of both sides, you bring down the exponent as a coefficient, and you solve. So I'm going to say that again because those are the major 3 steps. You get it to the form number equals power, you take the log of both sides, and then you bring down the exponent as a coefficient and solve for the variable. Okay, so in summary here, if you have, this is from the exponential formula, so if you have 2 powers that are equal to each other with the same base, then that means the exponents are equal to each other as well. If you have 2 sides that are equal to each other, then taking the log of those 2 sides is equal as well. Okay, so until now, we have only been able to use calculators to evaluate logarithms with base 10. So look down here at example 2. So until now, something like log base 2 of 45, we've had to use guess and check, like 2 to the power what equals 45. So now I'm going to show you how to use your calculator to get the exact answer. So this is a little bit of a tricky explanation. So I'm going to invite you to just copy this down. and then I'll explain it. So if you need to pause the video, you can. Okay, so we start with the fact that these are two different ways of expressing the same thing. So this recall thing up here is just like, remember that log base b of x equals a is the same thing of saying b to the a equals x. So those are equivalent statements. So we're going to start with this equation, okay? So x equals b to the a, and we're going to take the log of both sides. So that's, oops. So I'm going to write that here. So the first thing we did was take the log of both sides. So then in this next part, I bring down the exponent as a coefficient. Okay, so using the laws of logarithms. So notice I just brought down the a down to party with everybody else. Then I, in this next line, just solved for a, or isolated a. So I divided both sides by log b. So now look, a is equal to log b over log x. But we also know that a is equal to log base b, sorry, that's supposed to be base b of x. So that means that these two are equivalent. So log x divided by log b is also log base b of x, since they are both just two different ways of representing a. So because they are both equal to a, they are equal to each other. So that brings us to our change of base formula. So if you have log base b of x, I just realized this is written really poorly, so I'm going to redo it. If you have log base b of x, then you can find that by just doing log of x, not logs, log of x divided by log of b. Okay, so for example, if you have log base 2 of 45, first think the answer should be between 5 and 6, because it's saying 2 to what power is 45? 2 to the power 5 is 32, 2 to the power 6 is 64, so it's somewhere in between. So to do this in your calculator, in this case, I'm going to annotate. Log base 2 of 45, you simply do log of 45 divided by log of 2, and the calculator spits out the answer, which is approximately 5.49. There you go. No more estimation, no more going back and forth, just straight up calculator does it for you. So recall that this means the same thing, that 2 to the power 5.49-ish is equal to about 45. Okay, so that's how you use your calculator to find that stuff. All right, so a few tips and tricks before we go on to do a few examples. Okay, this factoring thing, oh boy, guys, like most students struggle with this a little bit. So please, the best way to figure this out is to practice. So when you see something like this, okay, so this looks differently than, like, if we had 3x plus x, it's pretty easy for us to common factor out an x. So we would have x is 3 plus 1. Okay, or we would just collect like terms to be 4x. Something like this is a little bit more challenging. So we see this and it's not as clear just because we're not as used to working with exponents. But you can common factor out a 3 to the power x. Now, why can you? Well, because remember that when you multiply, so when I go back to expand, 3 to the x times 3 to the negative 2, what is that? Well, those are powers with the same base. So that's just the multiplication rule, and you add the exponents. Okay, so the way that I understand this is I just do it and then I multiply back and make sure I get back to the original. And then of course 3 to the x times 1 is just 3 to the x again. Okay, so another way you can think about it, if you don't like that, is when you are factoring out a 3 to the x. Actually, no, I'm not going to do that one. That one doesn't make as much sense. That's just the way I do it. Okay, sorry, I don't want to over confuse you. There is another example coming up where I show this, so hopefully that helps you. But and I will do some examples in class again with that. All right. Also, just remember the general form of an exponential equation. So I'm going to annotate, but it gets so, it's just hard because it takes up so much space. So just remember A is your initial value. Okay, it's what you start with. X is your number of periods. But B is really important to remember. So B is equal to 1 plus your rate of growth, if you're dealing with growth, or B is equal to 1 minus your rate of decay, if you're dealing with decay. So if you have 6% growth, for example, then B would be equal to 1.06. But if you had 6% decay, B would be equal to 0.94. Okay, so growth, it's 1 plus the rate. Decay, it's 1 minus the rate. And to me, that would make sense because, like, if you're decaying 6 by 6%, that means you're always multiplying by 94%. You're always 94% of what you used to have. Okay. Then we have these generic formulas for half-life, compound interest, and doubling. Okay, H is the half-life time, D is the doubling time. These P's are the initial, this A is the initial. And just again, going the generic way to take the log of both sides to solve exponential equations. So when you get to the form a number equals a power, you take the log of both sides, you bring the exponent down, and you isolate the exponent. Okay, so example 3, I have A and B. I'm going to solve A first. Now I'm going to try to do this using, because drawing it with annotate was challenging. So I'm going to try to insert equation, but sometimes, yeah, see, Word puts it in the middle. So I'm just going to completely solve A. You just make sure you're doing it under A. Then I'll erase that and completely solve B. Make sure you're doing it under B. Okay, so here is a case again where we can common factor out. So 2 to the power x, 2 to the power x can be factored out. So when you factor out 2 to the x from this, you get 2 to the power 2. Now again, why is that? Well, because when you multiply 2 to the x times 2 to the 2, you will get a you will add the exponents to get 2 to the power x plus 2. Okay, and then I'm subtracting 1, since 2 to the x times minus 1 would be minus 2 to the x. Okay, so I've common factored out a 2 to the x. Now what's cool about that is that when I common factor that out, I am left with just a number in the bracket. So 2 squared minus 1 is just 3. So now I can divide both sides by 3. And now I can solve. Now, this one is pretty easy to eyeball. Okay, 2 to the power what equals 8? The answer is 3. However, if A, your brain wasn't functioning and you forgot that, or if this was a more challenging question, what you would do now is take the log of both sides. So take the log of 2 to the x, set it equal to the log of 8. Okay, so then your next step would be to bring the x down as a coefficient. So x times log 2 equals log 8. And to isolate x, by dividing both sides by log 2. Of course, I have to always worry about formatting on here. Oh, sorry, my bad, it's log 8. Sorry guys, log 8 divided by log 2. Okay, and if you put that into your calculator, you get 3, which is the answer. Okay, which I don't know why it's going over there. See, this is what I mean, kind of drives me crazy. All right, so that is example 3A. Now we're going to go to example 3B. So believe it or not, we are now mixing quadratics with exponentials. So I'm going to first move the 6 over and then show how you can recognize that this is actually quadratic techniques in disguise. So I'm going to move the 6 to that side, equaling 0. Okay, so again, to your eye, this isn't automatically a quadratic, but it is, okay? So this is actually of the form, you can write this on the side somewhere, a squared minus 5a plus 6 equals 0, where a is equal to 3 to the power x. Okay, because think about it, then that means a squared is 3 to the x squared, which is 3 to the 2x, right? That rule says we multiply the exponents. And then we have 5 times 3 to the x plus 6. So we need to factor this just like we would this equation, which factors to a minus 2, a minus 3. Okay, but in this case, a is 3 to the x. So we're going to insert an equation here. So we have 3 to the x minus 2 times 3 to the x minus 3 equals 0. So that leaves us with 2 equations now to solve. Okay, so 3 to the x equals 2, and 3 to the x equals 3. Okay, so one of these is simple to solve. One will take a little bit more work. Okay, 3, sorry, I'm just getting a different color because, you know, we like some color. 3 to the x equals 3, that is just x equals 1. Hopefully you guys can all just do that kind of in your head. But 3 to the x equals 2, we have to actually use our log thing to solve that. So we take the log of both sides. Okay, bring down the exponent. Isolate the variable, so log 2 divided by log 3. And you get out your calculator, punch that in, and you get 0.631. So that means that 3 to the power 0.631 is equal to 2. So these are your 2 solutions. So this equation has 2 solutions, 1 and 0.631. All right. Well, let's move on. Okay, we have 2 more examples. Example 4, and then we have a word problem in example 5. So this one I'm going to attempt to do, no, I will do it with the computer. I think it'll look nicer. Okay, so first things first, notice that we have, I apologize for that. We have a power equaling a power. So when we have that, we can actually go ahead and take the log of both sides, okay? If there were any other numbers or coefficients being added or subtracted around, we couldn't, but we just have a power equaling a power. So I'm going to take the log of both sides. So 2 to the power x plus 1 is equal to the log of 3 to the power x minus 1. Okay, so yeah, by the way, if your example said x plus 2 here, this should actually be x plus 1. So if I didn't change that in your note, then please go ahead and change that. That's my mistake. Okay, so we took the log of both sides. So now we can bring down the exponents, but we have to be careful here because the exponent is x plus 1, which means all of that has to be in brackets. Okay, because then we're going to need to distribute that. Okay, this is the step that students get a little bit forgetful with or sloppy with or whatever word you want to use. So be very careful. So now we need to expand. So we get x log 2, x times log 2 plus log 2 equals x times log 3 minus log 3. Okay, now I want to be, this is where students often like, okay, they get up to here and then they're like, how on earth do I solve for x? There's an x on the left, there's an x on the right, there's logs, like what do I do? So let's go back to the good old days of grade 9. Remember that log 2, these things are just numbers, right? That log 2 is just a number. So we only have one variable here and everything else is numbers. They just don't look like numbers because we're not used to seeing that. But let's pretend that this was like 2x plus 2 equals 3x minus 3. What would you do? You would move the threes, sorry, not the threes. You would move everything with an x to one side and you would move everything that's just a number to the other side. So that's exactly what we're going to do here, folks. So I often like rewrite it like this or something just to remind myself of what I'm actually doing and what techniques are available to me. So I'm going to do x log 2, sorry, minus x log 3. So now both of the things with x are on one side, and then minus log 3 minus log 2. Now both of the numbers, the logs are on that side. Okay, so on the left side now we can common factor out an x. Now, why is that just the best thing ever? Because now we only have one x, which we can solve for. So we're common factoring out the x. Okay, so hopefully now you can see the road that we're going on. So to isolate x, you divide both sides by what's in the bracket there. So I have minus log 3 minus log 2 divided by log 2 minus log 3. They look almost the same, but they're not actually. So that's what you get. And you put that into your calculator. And you're very careful with your brackets and what's on the top and what's on the bottom. Hopefully you guys know all that by now, and you get approximately 4.419. So please actually take a second to put that in your calculator and make sure that's what you get, because if you're not getting that, you need to talk to me in class to make sure we get your calculator stuff under control. All right. One more question. This one is actually the simplest. So it's a question again that we were used to seeing, but now we can solve it with logs and get the exact right answer. So we have an investment of $2,500. It grows at a rate of 4.8% per year, compounded annually. When will the investment be worth $4,000? So we want to set up our equation. So we have $2,500 that's growing. So we have 1.048 to represent a growth rate of 4.8%. And we don't know, though, how many periods have happened, how many years, when it will be equal to 4,000. So again, this is what we used to have to estimate with No longer. We are in the land of the logarithms where life is exact and beautiful and perfect, and we just work. We work the algorithm. So we can't take the log of both sides yet. We need to divide both sides by 2,500 first. So 4,000 divided by 2,500 is 1.6. Now we take the log of both sides, okay? You guys will get so used to doing this that you'll be able to do it in less steps, okay? I'm only showing you this many steps because we are learning. Okay, taking log of both sides. Now what do? I bring the x down as a coefficient, not an exponent. Yay, my unknown is down with everybody else, which means that I can isolate him. Life is good. I'm only a minute away from being able to move on. Okay, so x is equal to log of 1.6 divided by log of 1.048. And that is just calculator work, my dear students. And you get an answer of 10.025. So then you can write a beautiful sentence. Therefore, the investment will be worth $4,000 after 10.025 years, or you can say just after 10 years, or if you want, you can turn 0.025 into number of days. 0.025 times 365 days in a year is like 9 days. So 10 years, 9 days, depends how, like, you know, specific you want to be, how much you want to show off your beautiful knowledge. And that, my friends, is exponential equations. Hopefully you took something away from that, understood it. Come to me with your questions, come to me with your queries, your curiosities, and I will do my best to answer those. Okay, so thanks for watching, and I hope you learned lots.